We spoke about the explicit and implicit schemes for solving the uh, advection dispersion equation. So let me just quickly go back and just spend maybe a couple of minutes on that. So the explicit scheme, we have a straightforward algebraic equation which can be solved sequentially for every value of I from 2 to n minus 1. Uh, Remember, we are dividing up the domain, which goes from x equal to 0 to x equal to L into n boxes of equal delta x. Okay, so each of these boxes has got the same grid spacing delta x. When I do that, at x equal to 0 and at x equal to infinity, the boundary condition is already defined, right? So we already know the answer. Out of these n cells, we already know the answers in cell number 1 and cell number n. So the unknown, the concentration at every time step, is not known at cell number 2 to cell number n minus 1. Okay, so we write this equation that I've written over here, which is the numerical approximation of the partial differential equation, right? So please keep in mind the original partial differential equation is dou c by dou t equal to minus vx dou c by dou x plus d dou square c by dou x square. That is the original equation that we are trying to solve, right? But when I want to solve that, I cannot solve that equation unless I break up my domain into these discrete boxes, right? And then write the equation in a numerical form. So the second line, the equation that's written in the blue font, that is a numerical approximation of the first equation, right? The red font is the actual equation, and then I'm approximating it. So please keep this in mind. These two equations are not equivalent. The numerical equation is an approximation of the partial differential equation. Okay. So anyway, so when you look at this equation, there is only one unknown, which is the concentration in the ith cell at time step t plus delta t. All other terms are known in that equation. So what you can do is you write this equation for I equal to 2, I equal to 3, I equal to 4, and so on up to I equal to n minus 1. And each of these equations can be solved because there is only one unknown in that equation. So that is the explicit scheme. Okay. For the implicit scheme, on the other hand, we write the numerical approximation of the equation in such a way that for every equation, there will be three unknowns, right? So Ci minus 1 is unknown, Ci is unknown, and Ci plus 1. All these values are written at t plus delta t time step, which is the next time step. So I know the concentrations in the previous time step, which is based on my initial condition, and then we watch the solution evolve as a function of time, right? So t plus delta t, concentration at t plus delta t is not known, and it's not known at all of those different cells, I equal to 2 to I equal to n minus 1. So therefore, in this equation, I have three unknowns. So what happens is you cannot solve this equation uh, using the traditional approach, where you have these different coefficients of the different terms, Ci minus 1, Ci, and Ci plus 1. Those coefficients are not, uh, 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 although you can calculate them, you can't solve them sequentially. So what you have to do then is to write the system of equations for all those values and then solve them simultaneously, right? So because you have uh, n minus 2 unknowns and n minus 2 equations, yeah, so you'll have to solve those equations simultaneously. All right, so when you do that, I just quickly demonstrated that in the previous class. Don't worry about it. You don't have to memorize all of these steps. So what happens is you get a system of equations which can be written in matrix form as A times C equal to B, where A is the coefficient matrix of the concentrations at cell 2, 3, 4 up to n minus 1. and then B, which is the right hand side, is the forcing vector, right? So you have all of those, and then you write, you solve for concentration C as A inverse times B. Now this A inverse can be computed. There are many different schemes available to compute the inverse of a matrix. I'll not get into all of those details, but the general procedure for solving the implicit scheme is computationally a little bit more intensive than the explicit scheme. Now, the advantage with the explicit scheme is that it's simple to solve. It's an algebraic equation. All you need is basically a calculator. You can solve it. But the implicit scheme requires you to invert a matrix, and it's not possible by hand, right? I mean, if it's a 3 by 3 matrix, maybe you might be able to find the inverse, right? But once the size of the matrix becomes large, it is practically impossible to invert that matrix by hand, right? So typically you have to depend on some kind of a computational a software or a computational tool to help you to find the inverse of the matrix. Of course, these days it's not a big deal. So you can all of these different MATLAB, Python, and all of them can easily invert the matrix for you, and then you have the solution to the problem. Now, the other uh, advantage slash disadvantage is that in the case of the implicit scheme, the scheme is stable for all values of delta t, right? The time step can be anything, and the implicit scheme will is always stable. The explicit scheme, on the other hand, does has it has a stability criterion that has to be satisfied in order to ensure that the solution does not blow up. Okay, so this is the stability criterion for the explicit scheme. The time step that you choose has got to be less than the value that you compute using this, right? Delta x is known, d is known, and vx is known. So you can put in all those numbers here. You will get a certain value of delta t. You have to make sure that your time step is always less than whatever this number gives us. Okay, so only in that situation, the explicit scheme will give you stable solutions. Okay, now in the next couple of slides, I'm going to show a comparison between the solution. Okay, we'll get to a problem first, and then we'll get to the solution. Okay, so I'm going to show you a numerical problem. Now again, this numerical problem involves uh, certain parameters, which again might not necessarily be something that you can memorize and so on. So don't worry about it. Let's just get to it. Okay, a chloride solution with a continuous concentration of 600 mg per liter enters an aquifer along a line source. Determine the chloride concentration at a distance of 25 meters from the source after 1, 2, and 4 years. The aquifer parameters are K equal to so and so, hydraulic gradient is given, the porosity is given, and the effective diffusion coefficient is also given to us, right? So all of these different parameters are given to us. So what you can do is you can first find the velocity in this particular problem. So that will be k times dh by dx divided by n, which is the porosity. So k is given, the hydraulic gradient is given, so you can, and then the porosity is also given. So you find out v or vx like we've been using, and then you take that vx and put it into this equation, dou c by dou t equal to minus vx dou c by dou x plus d dou square c by dou x square. Like I said, you have the analytical expression for this, and you also have a numerical expression for it, right? So we will look at how to compute all of those different parameters. Let's just go through the steps. So v is given. So once you find v, then it allows you to find uh, what the dispersion coefficient is, because remember, what is given to you is the effective diffusion coefficient, d star. If you remember from the previous uh, lectures, we spoke about the difference between dispersion and diffusion. So in this case, what is given to us is the effective diffusion coefficient. And once you find the velocity, you can use the longitudinal dispersivity to find out the dispersion coefficient. So D, dispersion coefficient, is alpha L times V. Now this alpha L is what is called the longitudinal dispersivity. We have spoken about this in previous lectures. So for that, there are there are some kind of empirical relationships are available. Again, don't bother memorizing all these. So alpha L you use that in this particular problem, and then you figure out what alpha L is, and then once you have that, you can find out the dispersion coefficient, and that comes to around 10 power minus 7 meter square per second. Okay, now you will notice that the diffusion coefficient is of magnitude 10 power minus 9, and what we are getting here is of the order of 10 power minus 7, which is what I said earlier also, that the diffusion coefficient is so small that, you know, the dispersion coefficient is not changed much just because we have information about the diffusion coefficient. For any practical purposes, it's just there, but it really doesn't change the answer as such, right? It's 100 times smaller than the dispersion coefficient. So whether the answer is 100 or 100.01, it really doesn't make much of a difference, right? So anyway, so that is the relative importance of dispersion versus diffusion, which we've already spoken about. Okay, now we have all the parameters needed to solve the problem, right? We have V or Vx. Okay, to be more precise, we should probably refer to this as Vx. I'll do that since we've been using that consistently all these, right? We'll just put Vx over here. So then now after we've computed Vx and we have D, now it becomes possible for us to solve this equation, the partial differential equation, both analytically as well as using the explicit scheme or the implicit scheme or whatever it is. Okay, so I'm going to show you yeah, well, the analytical expression simply looks like this: C equal to C naught by 2 complementary error function x minus Vt. Okay, again this should be Vx. Okay, all of these are Vx. It doesn't make much of a difference whether you write it as V or Vx because it's a 1D problem. But since we've been using Vx, I'm just going to continue using that. It's not a major issue. Okay, anyway, so now what I'm going to do is I'm going to show you a plot which compares the analytical solution with the numerical solution. So now this has been obtained from an Excel file. I'll show you the Excel file shortly, but just take a look at what the solution is telling us. Okay, so these squares that you see, those are the analytical solutions, and then the solid lines, those are the numerical solution. Okay, and you will see that the numerical solution seems to be fairly uh, uh, fairly close to the analytical expression. The analytical expression or the analytical solution is assumed to be the truth. Okay, so and then the numerical solution, like I said, is only an approximation for that truth, and it depends on what kind of time step you use and so on. And you can also notice that there are some points, maybe somewhere over here. That if you look in this region, you can see that the numerical solution and the analytical solution are not falling right on top of the other, right? So it's obviously the numerical solution is not an exact solution; it is an approximate solution, right? Whereas in this case, the analytical expression is an exact solution, right? It's based on an analytical expression. Okay, how we got this, I'll show you. I have an Excel file where I show how this is computed. I'll show you that. Now, does the solution make sense to you? That the concentrations at 1 year and then 2 years and then 4 years at a particular, remember this is on the x-axis, I've got time, distance on the x-axis, right? And if you go back to the problem statement, it says determine the chloride concentration at a distance of 25 meters from the source. Okay, so 25 meters from the source would be somewhere over here. This is 25 meters of the source. So after 1 year and after 2 years, the concentration is pretty close to zero, right? After 4 years, you start to slowly see some kind of a low concentration with respect to the 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 source concentration. The source concentration is 600 mg per liter. Okay, so once you get the numbers from here, you'll have to multiply it by 600 to get the actual concentration, because the y-axis is C divided by C naught, right? It's not the actual concentration, it is the relative concentration, C divided by C naught. That's why it goes from 0 to 1. And then so once you get the number from here, the fraction from here, you have to multiply it by C naught, let's say 600 mg per liter, to get the actual concentration itself. And it turns out that at this particular location at 25 meters from the source, the concentrations are very low even after 4 years. Okay, but intuitively, does the solution make sense to you? Is the solution basically what you expect? Will the concentration increase as a function of time? That's my question. At a particular point, do you expect the concentration to increase as a function of time or not? Okay. Anybody has any thoughts?
So the concentration should always decrease. It will never be the same. And it
As a
shouldn't
function of time,
as a function of time, yes.
the concentration should decrease.
Because it's spreading out. That's
Ah, okay. So good point. Let's just go back and read the question. Okay. A chloride solution with a continuous concentration of 600 mg per liter. That is the condition.
got it.
So the source is always being provided at 600 mg per liter. Okay.
Yes, source
Yeah.
is there.
Thank you. Yeah. Thank you. That's an important, because you're maintaining the concentration at the source at 600 mg per liter throughout. And this whole approach assumes that. Okay. Yeah. Thank you. Okay. So now what I'm going to do is the next plot is showing as a function of time at different points in space. So the red line, the red curve, is showing how the concentration changes at x equal to 5 meters, at x equal to 10 meters is green, and then the blue line is at x equal to 20 meters. Now, does this follow what your expectation is? What you should do is look at any one of the curves, and let's say the red curve, for example, for some time after the flow starts, after the concentration, the source concentration appears, the concentration at x equal to 5 meters is 0. And then after some finite amount of time, it starts increasing from 0 and starts going up and up and up until it reaches close to its asymptotically, it is approaching concentration of 1. I mean, the relative concentration of 1, which means it is approaching the 600 mg per liter because it is very close to the source, right? The source is at x equal to 0. At x equal to 5 meters, the concentration, if the source is continuously providing 600 mg per liter, as you get closer and closer to the source, the concentration keeps increasing until asymptotically after some time, maybe it'll just reach 600 mg per liter. Okay, like I said, what is shown on the y-axis is C divided by C naught. So to convert it to absolute concentration, you have to multiply whatever number you get from here, you have to multiply it by 600 to get the actual concentration, right? So if it's 0.5, that means it is 300 mg per liter. If it is 0.2, then it is 120 mg per liter, and so on. Okay. Now, if I move a little bit further away from the source, so from x equal to 5, I go to x equal to 10, I see that it remains at 0 for a longer duration and then starts to increase, and then it is asymptotically again going towards 1 or 600 mg per liter, but it is not as close to 1 as the red line is, which makes sense, right? Because the farther you are from the source, the longer it will take to reach that source concentration of 600 mg per liter. And then the third curve, of course, is just an extension of the same thing. When you are 20 meters away, it remains at 0 for some time, and then slowly starts to increase, and then by sometime 3 into 10 power 8 seconds. 3 into 10 power 8 seconds would be how many years or days? How much would it be? Anyway, let's not worry about that. Anyway, so the point being that as you move away from the source, the time it takes for the concentrations to start increases, of course, and then it also takes a long time to reach the C by C naught of 1, right? The farther away from the source you are, the more time it will take for the concentrations to reach the peak value or the source value. Okay, so this is what this is telling us. Now I will also share now, just hold, let me share the Excel file which I used to compute this. I'll just quickly demonstrate what this Excel file is doing, right? So C naught is 600 ng per liter. Let me put that ng per liter. The velocity is 10 power minus 7 meters per second. I've put that in. The dispersion coefficient is 1.9 to 10 power minus 7 meters square per second. And x, okay, anyway, x is 1 meter, whatever it is. So at 1 meter, I'm just computing these numbers. Then, okay, I'll go to sheet 2, where what I've done is I've taken the domain and broken it up into cells of size 1 meter, right? Dx is 1 meter. The length, the total length of the domain that I have chosen is 50 meters. Okay. Remember, at x equal to infinity, concentration is supposed to be 0. But in this case, I'm choosing the domain of size 50 meters because you have to pick some finite size of the domain, right? You can't just say that, I'll compute up to infinity, because then it's not possible. Physically, it's not possible for us, right? So all the parameters are there, and then I compute the, now this what I'm showing in this sheet is the explicit scheme. So therefore, there is a maximum time step that's allowed. Okay, zoom in a little bit more. So I compute the maximum time step allowed using the delta t divided, delta x divided by 2v by delta x plus d, or whatever it is. We have used that formula to figure out what the maximum time step is. The maximum time step seems to be 2.08 into 10 power 6 seconds. That's the maximum time step allowed. So if the maximum time step allowed is given to us, then we can use any time step that's, as long as it's less than that, it doesn't matter. So we have chosen a time step of 2 into 10 power 6. Okay. And then I mean, you can, when you look at this Excel sheet, you can easily understand what's going on here, right? I'll share this Excel file with you so you can also play with it and see what happens when you change the value of the delta t over here, right? So if I change this, everything will start to, if I make it 2.1 into 10 power 6, okay, second. If I make it 2.1 into 10 power 6, the values will start to, right? So you see there's a greater departure from the, and if I increase it further, you will start seeing, oh, see, the solution has blown up. So it's no longer able to give us. So even something as low as 2.1, even 2.5 might also give us trouble. Okay, after 2.5, it's still okay. It's still able to do something. But if I increase it even further, the solution really starts to become unstable. And then, like I said, you see, now the answers are deviating from the actual solution, right? Anyway, so obviously we're not supposed to do this. So I'll just go back to the original. And once you do that, then everything falls in line. Everything is okay. Everything's good, right? But when you play with it, it starts to misbehave if you don't give it the right parameters. Okay. Anyway, so I'll share this Excel file with you. I urge you to just go through it and understand the logic behind how the explicit scheme is being calculated and so on. We already have the equations. I've just translated that into these different cells that have been used in the model. Okay. All right. So let me just go back to the PPT. Okay. All right. So now we've spoken about the uh, explicit and implicit schemes, and I've shown you the Excel file which is shown how to solve this and so on. Okay. Now we are going to move on. Okay. Any questions before we move on to the next topic? Okay. No questions. I presume. All right. So the next topic that we will discuss in the context of contaminant transport is sorption. Now, this sorption is basically a short form for saying adsorption. Okay, so you can think of it as, it's basically adsorption, which is when the contaminant gets attached to the surface of the soil, right? So I have the soil particles, and some portion of the contaminant gets attracted to the surface of the soil, and then it remains on the surface of the soil, right? So remember, when we wrote our advection dispersion equation, we had a box, a control volume, and we were trying to figure out how much mass is coming in and how much is going out and so on. Now remember, inside this box there are soil particles, right? Different soil particles, whatever it is. Okay. Now the water is coming in with some concentration into this box, and it is leaving this box at some other concentration, right? That's how we set up the equation for that, right? So the water that's coming in, right? So that is the concentration of the contaminant. There is the concentration of the contaminant in the water, right? So that is how we define this concentration C. Now there is also the concentration of the contaminant due to adsorption. Some of those contaminant, or this whatever is present in the water, may also get attracted to the soil particles and get attached to the surface of the soil particles, right? So when that happens, when you're writing a mass balance for this box, remember what we are doing is to write a mass balance for how much concentration came into this box, or how much contaminant came into this box, how much contaminant left the box. And when you balance it, you can say that there must be an increase of concentration of this contaminant inside the box. Now, as long as we were not talking about adsorption, what we meant was how the concentration of the contaminant was changing in the water alone, right? We were not worried about the soil particles. Now, please remember that not all contaminants get attracted to soil particles. Okay, or in other words, I can say not all soil particles attract contaminants onto their surface. Okay, so there might be different extent of sorption on different types of soil particles and so on. But in general, if you don't include adsorption, you are assuming that the particular type of soil that you have and the particular type of contaminant that is present in the water, they don't have any attraction for each other. Okay, so if I have a particular type of soil and a particular type of contaminant, if these two don't have any attraction for each other, you don't have to include adsorption. Okay, the only situation when you will have to include adsorption is if the soil is attracted to the contaminant, or the contaminant is attracted to soil. Either way around, whatever, whichever way you want to say it. Okay, but the net result is that the contaminant that is moving into this box and then leaving the box is going to leave behind some of the contaminant, either either as a change in concentration of the water inside this box, or a change in the concentration of contaminant that is adsorbed on the surface of the solid, right? You can think of it like this. um, Let us say, well, just now we had Diwali and all of that, right? So usually what happens is, when when there is a when there's a high concentration of these uh, smoke and the okay, smoke and whatever chemicals are present in these crackers that are burst, right? um, you can, if you put your clothes out to dry, okay, and then if you bring the clothes back in after they've been exposed to this uh, air that is contaminated uh, with these chemicals coming from the crackers and so on, you can smell that on the clothes. I don't know if you've experienced it. I have actually experienced it, right? So if you bring the clothes from outside where they are exposed to the atmosphere, and the atmosphere is thick with smoke, right? You can smell those contaminants on the very surface of the cloth. Okay, so something similar to that, right? So I have a box. I mean, when I'm saying a box, it's an imaginary box, right? I've drawn a box around a portion of the soil, and some contaminant is moving through that. Now, what we are saying is that when you write the mass balance for this box, right, the concentration of the contaminant the contaminant is present both in the water and on the surface of those soil particles. Okay, let me just use a different color to denote that. Let's say the contaminant is getting adsorbed onto the surface of the soil particles, right? So you'll have on the surface. Okay, when I say although I'm drawing some dots on the inside, you can imagine some kind of a three-dimensional surface where these little uh, blue particles that I've drawn, those are being attached to the surface of the soil. Okay, maybe it was not a good idea to draw it inside, but anyway, I hope, I'm assuming that you understand what I'm trying to do, right? Some of these contaminants are getting adsorbed on the surface of the soil. Okay, so how do I express that contaminant of that concentration, right? So what I do is I denote that concentration as CS, which is the concentration of the contaminant on the solid or the soil particles, right? The concentration of the contaminant in the soil or in the solid, right? So a portion of it is in the water, and some portion of it is present as these molecules attached to the soil surface. So how we mathematically define that? So this concentration CS, right? We can define it as the mass of contaminant on the solid, mass of contaminant on the solid divided by, sorry, okay. So that's the mass of the contaminant on the solid divided by the mass of the solid itself, right? So if I have a soil particle uh, which has a certain mass, and then there are some contaminant particles which are attached to the surface of that soil particle. So this concentration is defined. We are defining it in this manner. We are defining it as mass of contaminant on the solid divided by the mass of the solid, right? But if I want to remember, this concentration has got units of ml minus 3, right? It's mg per liter or kg per meter cube and so on, right? But this one, I have got a mass in the numerator and a mass in the denominator. So the CS cannot be directly used in that equation along with C, right? Unless I have it in the same dimensions, ml minus 3, it becomes difficult to incorporate it into the equation. So what do I need? I need to, so if I multiply this, um, what do I multiply it with? If I multiply it with the bulk density of the soil, right, rho B, which is the mass of solid per unit volume, that will give me mass of contaminant per unit volume uh, 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 of that particular soil sample, right? So if I multiply it by rho B, what is rho B? Rho B is the bulk density, right? Which is, so if I multiply rho B by CS, I will get the mass of solid. Sorry, my handwriting is terrible, really. Divided by the total volume multiplied by mass of contaminant divided by mass of solid. So if I do that, then there's mass of solid in the numerator and denominator, they get cancelled out. So you get the mass of contaminant divided by the total volume. So now you will this will have dimensions of ml minus 3. Okay, so then rho b into cs is something that I can use directly along with c, right? When I write the when I write the mass balance for this box. Okay, so that's what we're going to do now. Okay, so far so good. Uh, you understand the motivation for multiplying it by the bulk density, right? Because cs does not have the same units as c, so you can't just add another term with cs because cs does not have the right units. So to convert it to the right units, you need to multiply it by the bulk density of that particular soil sample, and that allows you to get units which are consistent with the concentration, right? So when I include this in the mass balance, remember my mass balance equation is simply mass coming in minus mass going out equal to accumulation or or the change, right? Or the change in storage, right? So we had what was that, minus Vx dou C by dou X plus D dou square. This in minus out, when you wrote it, you would have minus Vx dou C by dou X plus D dou square C by dou X square. I'm just coming to the last, uh, writing it in the final expression instead of going through all those steps. Okay, so you will get something of this nature, dou C by dou T plus dou CS by dou T into rho B. Now, if you remember, let me just quickly go back a few slides. Huh. So if you look at this equation, you divided both sides by the porosity, right? So you had an n on both sides of the equation. Now, if you were to write the rate of accumulation, the accumulation is happening both in the concentration change in the water. So here I have delta C. I would have to write it as delta CS, right? And then multiplied by rho B. But this n term would not appear there, right? Because the bulk density includes the total volume of that soil sample. So when I multiply rho B by CS, what I get is the total change in concentration in the soil itself, right? In the solid itself, in the entire volume. So I don't have to multiply it by n like I had over here, right? So because that extra n remains in that equation, now if you go back to that, you will recollect that, right? So this will have, there will be a divided by n over here. That's all. Okay, that is the only difference in terms of the mass balance that you get. So in fact, we are more used to writing it in the other direction. So you put this on the left hand side, dou C by dou T plus rho B by n into dou CS by dou T equal to minus Vx dou C by dou X plus D dou square C by dou X square. Now this is the equation for including sorption in the process, right? So but this also still is not very satisfactory to us because it is still not allowing us to solve the actual problem, right? So this is okay, right? So this is still not solving the actual problem for us, because now in addition to C, we have another variable in this CS, which we don't have really a very good idea about of how to obtain this value of CS, right? So to do this, we are going to do to find out what the CS is in terms of other values, we are going to use what are called isotherms. Okay. Now, this concept is simple to understand, but let us just imagine that I'm doing an experiment in the lab. Okay. I take a beaker, okay, fill it with water, and put some contaminant here at some concentration, let's say C1. Okay, I take another beaker, the same amount of water, and put some other concentration of the same contaminant, let's say C2. Okay, similarly, I'm just going to show three just for illustration, but imagine that I'm taking many different beakers, let's say 10 beakers with 10 different concentrations, C1, C2, C3, C4, and so on. Okay. Now, all of these beakers have got only water in them, and they are at different concentrations, C1, C2, C3, up to, let's say, C10. Okay. Now, what I do is I I drop a piece of soil, identical mass of soil, into all of these solutions. Okay. Remember, I'm taking a piece of soil, okay, and putting it, let's say, the same mass. If you put 5 grams in beaker 1, then you put 5 grams in beaker 2, beaker 3, and so on. Right. So an identical piece of soil is placed in beaker 1, beaker 2, beaker 3, and so on. Now, remember that why are we doing this? Because we know that this contaminant that is present in this water has got some affinity for the soil. Okay. So initially, when I put the soil into this water, the soil is completely free from any of this contaminant. The soil is a fresh soil sample. It has zero contamination on its surface. Okay. Then I drop it into this. What will happen is, slowly the contaminant which is present in the water will start to get attracted towards the soil. Right. So what will happen is, this concentration C1, C2, C3, those values will start decreasing as a function of time, and the concentration on the surface of the soil. Okay. So CS1, CS2, CS3, right? So let us call this CS1, the concentration of that contaminant on the soil surface. Let us call it CS1. Here it will be CS2 and CS3, right? So the C1, C2, C3, originally they were some value. It will start decreasing and asymptotically. Okay, so if I plot this C1 as a function of time in this particular beaker, okay, so I have time on the x-axis, I have C here. C1 started off here, and then it starts to decrease, and then slowly it'll asymptotically reach some constant value. Why is it decreasing? It is decreasing because the concentration previously used to be the contaminant present in the water. Now it's no longer present in the water. It is getting attracted to the soil particle and getting attached to the soil surface. Okay. Which means the concentration in the water is decreasing and the concentration on the soil is increasing. Do you agree with that? Before the soil is dropped, the concentration is present only in the water. Once I put the soil inside, some of uh, uh, the molecules of contaminant which are present in the water are no longer in the water. They have got attracted to the soil particle and they're attached to the soil particle now, which means the concentration in the water will decrease. Right? So let us say the concentration in the water becomes C1 star. At time t equal to 0, it used to be C1, and then it decreased, and after some time it reaches steady state, and so it stabilizes and it becomes C1 star. Similarly, here I'll have C2 star. Okay. Now remember, C1 and C2 are all different values. C2 starts off somewhere and then again becomes C2 star. Similarly, here I may have C3 star. Okay, this is important. I hope everybody is following along. That C1 initially started off high and then decreases and becomes C star or C1, C2, C3. All of these, they start off high and they decrease. Why do they decrease? It decreases because some concentration which previously used to be in the water is now getting attached to the soil. Okay, similarly C2, similarly C3, and so on. Now, if I plot this CS as a function of time, CS, what is the concentration of the contaminant on the soil at time t equal to 0? At time t equal to 0, there was no contaminant present on the soil. As soon as I put it inside, it starts attracting those those contaminant molecules onto its surface. So the concentration of on the soil sample will start at 0 and keep increasing, and then asymptotically it will reach some value. So let's call that CS1 star. Similarly, here I'll have CS2 star, and here I'll have CS3 star, CS3 star. And of course, if I have 10 beakers, I'll have C1 star, C2 star, C3 star, C10 star, and then I'll have CS1, CS2 star, CS3 star, CS10 star, whatever it is. Okay. Then what I do is I plot these C star with the CS star, C star with the CS star. Okay. And when I do that, I notice that these values seem to fall somewhat along a straight line. Okay, so assume that this line is a straight line. Now the slope of this line, we are going to call it KD. Now don't ask me why it's called KD. KD is called the partitioning coefficient, right? So KD is called the partitioning coefficient, right? So what is the relationship between CS star and C star? So basically CS star is basically KD times C star, right? The concentration in the water, sorry, concentration in the soil is KD times concentration in the water. That's what this equation is telling us. If the slope is uh, uh, if it passes through 0, let's say, so then it will be y equal to mx, right? And if m is the slope, or kd is the slope in this case, so y is cs equal to kd into c star, y equal to mx, right? So I get this expression. Now I'm going to take that back to this equation here. Remember, I had in this equation uh, this expression delta cs by delta t. Can we not replace this with kd times dou c by dou t? That's what we are going to do. Okay, so I'm going to go to this next slide. So I'm going to, in that equation, I'm going to write it as dou c by dou t plus rho b by n into kd into dou c by dou t. So this kd into dou c by dou t is nothing but dou cs by dou t, okay, which is what we had in this slide. If you look at it, I have dou cs by dou t, right? This term, I'm replacing it with kd into dou c by dou t equal to minus vx dou c by dou x plus d dou square c by dou x square. So which means I can write this as dou c by dou t into 1 plus rho b kd divided by n equal to minus vx dou c by dou x. Okay, now this 1 plus rho b into kd divided by n, this number is sometimes referred to as capital R, okay, which is called the retardation factor. Okay, so in other words, I can write this as dou c by dou t equal to minus vx by r dou c by dou x plus d by r dou square c by dou x square. So this is the new equation that I get, which is a modified form of the modified form of the advection dispersion equation, but it now includes the impact of adsorption, absorption, or retardation in the uh, in this. So in addition to accounting for advection and dispersion, this equation now also accounts for retardation or adsorption. Retardation is basically another word for adsorption. Okay, so the form of the equation is exactly the same. You just divide the coefficients dou c by for dou c by dou x and this dou square c by dou x square. You divide the dx by r and d by r, and then you get a new equation now, which in addition to two processes, advection and dispersion, also accounts for a third process, which is retardation. Okay, so we'll talk about what this means physically maybe in the next class. I think we are out of time now, so we will talk about the physical implication of what retardation means in tomorrow's lecture. Okay, so thank you very much. See you guys tomorrow at 9 a.m. All right, thanks a lot, guys. Bye bye, take care. Yeah, is there a question? Okay, all right, take care. See you all tomorrow. Bye bye.